I'm Serena.
And I'm Mayumi.
And today we will be teaching you how to write the definite integrals from limit expressions.
We can change limit expressions to definite integrals by observing the area under the curve of functions using rectangles. So let's say we have our function y equals square root of x, and we want to find the area under the curve using, let's say, 4 rectangles. So for this function, the n, which represents the number of rectangles, is equal to 4. And as you can see, this is an over-approximation since the rectangles of the portion of the area lies above the curve. So these regions are over-approximates to the actual area under the curve. If we were to change n from 4 to 6, so we increase it to 6 rectangles instead of 4, we can see that the total area under the curve becomes closer to the actual area. So we can shade in the extra area that goes off of the function. And as we can see, there is less total area that lies above the function than when there is a less number of rectangles. If we were to use an infinite amount of rectangles, we know that the area under the curve would be exactly the value of the integral, which represents the exact value under the curve of any function. We can represent this idea through a limit expression. So we know that the total number of rectangles is n, and to find the area of each rectangle, we know that it is equal to length times width. In this case, the width is change in x, so we can call this value right here as change in x. And we're going to make change in x equal to the starting point, which is a, and the ending point b. So change in x would be b minus a divided by the total amount of rectangles. In this case, it would be 4, which yields us the width of each rectangle. And now we want to find the height. So we can call this value x sub I. And x sub I is equal to the starting point, a, times the change in x, times I, which is the number of rectangles. So xi here would equal to x1, and we would find this by setting I equal to 1 and multiplying it by change in x and adding it to a to find this x value. And we want to evaluate the height at this x value, which would give us the length of this rectangle. So in order to find this height, we would plug x sub I into the function, which makes it f of x sub I, which is equivalent to height. So we have our height and we have our width, and now we want to take into account all of these rectangles to find the total area under the curve and not just one rectangle. So what we would do is we want to find an infinite amount of rectangles. So first we can start off by finding the area of one rectangle, which is f of x sub I times change in x. And we want to find the limit as the number of rectangles n approaches infinity. So this would be a limit function, a limit expression as n approaches infinity. And because we want to find the sum of all the rectangles, we use sigma to express the sum as from I equals 1, which is the starting point, to n, which represents the total number of rectangles of f of xi times change in x, which gives us the final limit expression representing the area under the curve. And because the integral from a to b represents the exact area under this curve, and we know this is equal to the limit expression, so we can equate this to the integral of f of x from a to b dx.
So the general rule from changing your limit expressions into integrals So first, you want to find your domain, or the endpoints of your integral, by using your change in x and your x sub I, which we can remember is b minus a over n for change in x, and x sub I is a plus I change in x. And these will help you find what to put for the endpoints of your integral. And then the second step is to substitute x for x sub I. The third step is to find your equation using x sub I. And then the final step is to substitute it all into your integral notation. So in this problem, like the last, we can see that there are x sub i's that we can sub with x. So for this problem, we can also do that, which means that for our f of x sub I, our equation is 4x sub I plus square root of x cubed sub I plus 3. And this is equal to f of x is equal to 4x plus square root of x cubed plus 3. Then we can substitute it into a definite integral since our endpoints are given to us. So this will be the definite integral on the points from 10 to 15, with our f of x being this equation. So in this problem, unlike the other ones, it's harder to see what your change is in the function. So we're going to have to do a little bit of factoring. So as you can see, they both have a constant over an n value, which can be factored out, which will give you 12 plus 8i over n, all times 1 over n. And this will be our new change in x. So that means that like the last one, our interval will be from 0 to 1. And then from here, you can see that it can be the same as 12 plus 8 times I over n, which is the same thing as our x sub I, which we remember as a plus I delta x, which is correct. So with this problem, we can say that f of x sub I is equal to 12 plus 8x sub I, and then xi is equal to x. So our final integral will be from 0 to 1 with our regular function 12 plus 8x delta x.
Sometimes we can change the change in x to be the same value as the change in x in x sub I. For example, in this equation, as you can see, what perceives to be as change in x is not the same as the change in xi inside the actual function. So what we can do is alter this expression in order to be a little more easier to work with. So we can rewrite this. So we keep the original 5 plus 3i over n to the fourth, but we can change 2 over n to 2 over 3 times 3 over n. And this works because the 3's can cancel out and we're left with 2 over n. And we have a 3 over n in the argument and a 3 over n as the change in x, making it easier to work with, and we can easily handle a constant. So from there, we know that the change in x is 3 over n. Since x sub I is change in xi plus a, and our change in xi is 3i over n, and the a is 5, we know that we must have a value b such that b minus 5 over n is equal to 3 over n. So the answer for b would be 8 to satisfy this expression. So therefore we know that our domain is from 5 to 8. So now that we have our domain,
from a equals 5 to b equals 8, we can find f of x sub I. So we know that x equals xi, and our xi equals 3I over n plus 5. So f of xi would be x to the xi to the 4th power. So in the end, we can substitute this into the definite integral. So it would be from 5 to 8 of 2/3, since we can't forget our constant that we factor out from 2 over n, times x to the 4th power dx.